Hi, and welcome to this brief introduction of EET 130 555 chip lab that you'll be working on. I just wanted to walk you through that lab so you have a quick view of how it'll go, and then you can go ahead and get started on it right away. So first of all, this is a 555 chip. I'm just holding it in my hand here so you can see the scale of it. And you can see upside down, there are pins coming out of it, and sometimes they need a little bit of straightening, so you want to make sure those pins are straight. And we're going to be using the digital trainer here, this nifty little instrument here that incorporates both a breadboard as well as power supplies and a bunch of other things going on there. So we'll be using that. And it's just like the breadboards that you're used to using, except it's got some other components right next to it. So what we want to do is when we insert pins into a breadboard, we want to straddle the pins on either side of the channel on that breadboard. So you can see there's a groove cut into it, that channel kind of between A, B, C, D, E, and then F, G, H, I, J. That's between those two is that channel. And we want to check the alignment of the pins before we go ahead and push them in. So you want to make sure the pins are actually ready to be pushed in the holes. Otherwise, that's the number one way that we go ahead and bend pins. We don't check the alignment of the pins before we push them into the breadboard. So we see here there's one of the pins is not ready to be pushed in. It's a little bit crooked. It's not ready to be pushed in the hole. So I just wanted to show you that that's the one you'd want to straighten, kind of tuck it back into the hole before you apply pressure to the chip. So now you can push it in, just push it straight down with your finger and all the pins will go in, and you can see that for example row 11 has one of the pins there, and that's where I'll be connecting all the wires. So here's the chip correctly inserted, a slightly blurry photo there, but you get the idea. The pins are all fully inserted into the board. Here it is from the other side, a little bit better focus, but you can see that all the pins are inserted into the breadboard. So we're ready to start the lab. So we have what we call a pinout or a pin diagram, and this is the 555 chip. You'll notice that in the diagram it has the same little notch at the top, and it also has the same circle dot that is kind of engraved in the chip. Both of those help us find which pin is pin number 1, and then all the pins go clockwise from that. So that's kind of an industry standard for all sorts of chips. You look for that dot, tells you where pin 1 is, and then all the other pins are numbered clockwise. And then you can see there's some letters next to that pinout, and it kind of tells you what those pins are used for. The most common ones obviously would be ground, and that's GND here in this diagram, and then the positive voltage, usually labeled VCC. So pins 1 and 8 purposely put on opposite sides of the chip so that there's less likelihood of a short circuit. Notice that the markings that help align the chip at the very top, and also the dot for ground or pin number 1, is basically as much as possible on the pin diagram, really the same as this photograph of the chip in the breadboard. So they're really not trying to confuse you. They're trying to make it as simple as possible for the engineer. So the dot in the diagram will actually, and the notch as well, will actually look like the chip itself. So what I've done here in this picture is I've taken those labels that we see on the pinout diagram, and I've actually put them on the photograph of the chip. So you can see what the name of the individual pins are on the photograph of the chip. So here I've gone ahead and zoomed out a little bit, and so now you can see that the rows of the breadboard are labeled in the same way as the pins of the chip. So that way I know that any wire that I insert in that row of breadboard holes labeled as number 1 ground, that will be connected to the ground pin of the 555 chip. So any one of those 4 holes that in row 11 on the left hand side of my breadboard will be connected to ground. Whereas any of the 4 holes in row 11 on the right hand side of my breadboard, they will be connected to pin 8 of the 555 chip, and that will be VCC or plus 5 volts in the case of the 555 chip. That'll be what we power the chip with, the ground and the VCC. So you can see all the rows of the breadboard are labeled just like the pinout diagram that you might find by Googling the 555 chip online. So notice that the lab circuit diagram that in your lab notebook or this lab assignment ignores the physical locations of the signal. So that's what you'll find in engineering, is that I'm going to draw the diagram of my circuit, of what it is I want you to design, without caring where they physically are located. Notice in the picture to the right, VCC is at the top coming out, and ground has a wire coming out of the bottom. But that's obviously not where they are located on the chip. So many times in circuit diagrams, we will not have the pins drawn in the same way as a pinout or a chip diagram. So you just need to understand that there's a mapping between the two. And also, it would be useful for you to notice that not everybody uses the same abbreviations. So, for example, on the left-hand side, the pinout diagram that I received from the manufacturer, it tells me that pin 5 is the control pin, but they've abbreviated it as CTRL. And then on the right-hand side, the picture from our lab assignment, which is a circuit diagram that was drawn by an engineer explaining how to build a circuit, they've labeled the control pin as being CON. So as long as you're putting enough letters in there so that people can figure out which pin you mean, I think it's quite obvious that, hey, pin 4 is the reset, and yes, in my circuit diagram, I've called it RST. So just be aware they're not going to be identical abbreviations. So here's where the 5-volt power is going to come from, and also the ground. So if we want to go ahead and attach the ground to our breadboard, we're going to unscrew that ground thread. It doesn't unscrew completely, but at least it unscrews it far enough so you can see this tiny half of a hole underneath it. And you can insert a copper exposed portion of a wire into that hole and then tighten it, and that will make a connection with a wire. So those are the two ways you can connect ground. You can either use a special banana pin which plugs into the hole at the top of that black post, or you can use that little half hole at the bottom of it and use a wire. So two ways to make the connection to those posts. I'm going to go ahead and connect the other end of that ground wire to the one of the rails, this blue rail that I've decided to use on my breadboard. And I'm going to do exactly the same thing for the plus 5-volt post. I'm going to connect that to the plus 5-volt rail. And please don't short them out, otherwise your instructor will have to replace the fuse. So don't short them out. Do you want to go ahead and test that with a digital multimeter? Make sure it really is 5 volts. There's nothing wrong with that. Always make sure. So here's that circuit that we're going to build in the lab. You can see there's the 555 chip and a number of resistors, capacitors. It's got a light bulb. It's got a ground. So we're going to need 2 capacitors. We noticed that in the diagram, and both of them have one side connected to ground. So here I've just gone ahead and put literally one of the pins in ground for each of those capacitors, and the other one just somewhere on the breadboard. One of the capacitors is going to connect to the control pin. You can see that in the upper left, cut out from the lab diagram. And I've used this brown wire to go ahead and connect to pin 5. You can see that in the lower right, the pin out of the chip. The control pin is located at pin number 5. So you can see I've put the brown wire into the row for pin 5. Similarly, the other capacitor needs to connect to 3 different things. And you can see that it's connected to the TRI, the THR, and a resistor. So I've got 2 white wires in row 45 of that breadboard, and I've got 1 resistor in there as well. So that first white wire is going to go to that threshold pin, and that's pin number 6. So you can see I'm inserting it there into the row of the breadboard for pin 6. And the other one is for the trigger. I'm going to go ahead and insert that in row 2 of the, the row for pin 2 of the 555 chip. And then finally, that 47 kilo ohm resistor is that third thing connected to that capacitor. And I've inserted the resistor there. Now that resistor I just mentioned is connected to two other things. The first is a 27K ohm resistor. You can see it in the photograph here. And that 27K ohm resistor, the other end of it is connected to the source of the circuit, sometimes called VCC, and both of them in this case mean 5 volts. So the source voltage or the VCC are used interchangeably. They mean the same thing. It's the power that's driving the whole circuit. So people don't like to have two different kinds of batteries in their devices. You know, oh, I need a 9 volt and a double A. So in general, we try and design circuits so that they all use the same DC power voltage value. So that's really what we're doing, is we're trying to use one single 5 volt source to power the entire circuit. The other connection from that 47 kilo ohm resistor needs to go to the chip itself, that DIS pin in your lab diagram. So I'm putting one of the wires here to connect to that resistor, and the other end goes to the DIS pin, pin number 7. You can see I've just inserted it there in that row. The not reset pin goes to the plus 5 volts, and notice that there's a bar either above the reset or below the reset. That means if I want to reset the chip, I would have to make it a 0 value because it's not reset. So by connecting it to plus 5, I'm not resetting the chip. Because 5 is a plus 1 or a true, and so I'm connecting true to reset. That gets inverted to be false, and so it's false. I do not want to reset my chip. So that's what that bar under the word reset means. Finally, VCC and ground are connected to power up the chip. You can see here I've connected pin 1 to the ground rail, the blue, and I've connected pin 8 using a tan wire, and I'm going straight to the plus. Now notice that VCC wire has got a little bit too much copper exposed. I don't really like to do that, but it's good to point out here. Don't have wires with a tremendous amount of copper exposed. As you see, the chip wiring gets pretty tight in there, and so it's much easier to touch two wires accidentally if you have too much copper exposed. The amount of copper exposed really shouldn't be more than the thickness of the breadboard, because we don't want a lot exposed at the top end, and also we don't want to push the wire deep into the breadboard accidentally and make some short circuits underneath the breadboard when the wire curves and starts touching things sideways. So just wanted to show you that. It's not really it's actually a good negative example. I don't really love having so much copper exposed on the wires. So the last connection is from the output, and that's pin number 3. And that's going to go to the hot lead of the oscilloscope. So the oscilloscope ground can be clipped onto that same post, or you can use a banana clip by putting that in the hole of the ground pin. A good mechanical connection is needed, so it really shouldn't rattle around. You should really feel that it's nice and solid, because you can't have a good electrical connection unless you've got a good mechanical connection. The oscilloscope display shows exactly what you're supposed to see in this lab. You can see that channel 1 has a 1.1 kilohertz frequency signal, and you can see also the 500 microsecond grid marks on the oscilloscope. I can see at the bottom of that display that M 500 microseconds is shown there, and also on the right hand side the digital scope has actually calculated the frequency for us at 1.1 kilohertz, and I can see that it's a 2.2 volt swing there, RMS. Remember, RMS on a square wave is pretty much the full swing of the positive voltage, because RMS is sort of the amount of power that that voltage can deliver. If, let's say, you were operating a toaster oven and it compares it to a DC voltage. So if I were heating a toaster oven, For example, with this 2.2 volt RMS signal, it would be the same heat generated by that toaster oven as if I put a 2.2 volt DC. Well, look at this signal. The signal is about 2.2 volts peak, or 4.4 peak to peak. So what are we saying about that? Well, I'm sorry, it says here 7.4 peak to peak because of that spike that appears there. But you can see, just counting the grid marks of 2 volts each square, it's about 2.4 volts actually the square wave. So what we're saying is that the toaster oven really views it as being a DC signal of its peak voltage because it's a square wave, and so whether it's a positive or negative, it's the same amount of heat coming out of that toaster oven. And so except for that little glitch where it goes from positive to negative, it's pretty much holding steady throughout the whole time. So that would be different from a sine wave that has the peak voltage times 0.7, because the sine wave is all curved and not spending all of its time at its peak voltage. It's just spending a little bit of time at that peak voltage. Okay, little digression there, but that's the oscilloscope display from your lab. You can see the measurements zooming in there of what your scope has measured. And I think that's pretty much all I wanted to cover. Go ahead and try it yourself, and I think you'll find it's quite an interesting lab.